thank you, the organizers and JDG. I always think of JDG as a gold standard for publishing a paper, and I've had the honor of having a couple of my papers in JDG. So I also want to personally thank Professor Yao for all his energy put into not just JDG but into supporting mathematics. I mean, I've been a colleague of Yao for, I don't know what, 30 years, something like that. And if I had 1/10 the energy of Yao, I would be, I don't know what. Okay, so let me talk about mathematics now. So what I'm going to talk about are some differential equations that have been proposed they first appeared in a paper by Karins, Vafa, and Witten a long time ago. And so what is the background for these equations? The realm is I have a four-dimensional Riemannian manifold, so it has a metric. And then I have a principal bundle over the manifold. And we're going to take the structure group to be SU2 or SO3. And what I'm going to say, and perhaps generalizes to other groups, but anyway, it's going to be this. And now if you have a metric in 4 dimensions, I'm going to assume this is also an oriented manifold. And so if you have a metric, then a bundle of 2 forms on X decomposes into what are called the self-dual 2 forms and the anti-self-dual 2 forms. And so these are, you have the Hodge star operator, and these are the plus eigenspaces, and the other ones are the minus eigenspaces of the Hodge star. So for example, if I were to take an orthonormal basis of 1 form's a point, then these guys would be spanned by things like this. And you get the rest by sort of cycling 1, 2, and 3 around, and then these guys would be spanned if you put a minus sign there. So that's the realm, and then what we're going to be interested in is solutions to a differential equation. And so the equation we're interested in are equations for a pair of objects. The first object is a connection on this principal bundle. And then the second object I'll call phi, which one thinks of what's going to be as a section. It's going to be a self-dual 2 form with values in the bundle associated with the Lie algebra of SU2. So we have the bundle quotient out by the adjoint action on the Lie algebra. So it's a 3-dimensional vector bundle. And so phi is a self-dual 2 form with values in that bundle. And the equations, so this is a kind of a, you can think of phi as kind of a Higgs field. And these are generalizations of what people call the Higgs equations, I guess, in dimension 2. And the equations are this. You look at the curvature of A. There are 2 equations. You look at the self-dual part of the curvature of A. So I put a plus up here to indicate that it's the self-dual part. And this is a certain bilinear function of the Higgs field. So I'll write it this way schematically with a semicolon as a bilinear. I'll tell you what that is in a minute. And then the other equation, there's an equation that involves phi, and it says that the covariant exterior derivative, which is a 3 form, should be equal to 0. And so those are our 2 equations. And now what is this bracket? This bracket, well, okay, so one can write it in invariant notation, which I find unbelievably irritating because if you actually have to do calculations, you're going to choose a basis anyway. So let me choose a basis, and then tell you what the components of this are with respect to the basis. So if I choose a basis A equals 1, 2, and 3 for self-dual 2 forms, then this is, well, you have the antisymmetric matrix ABC, epsilon ABC, and then I take the actual commutator of the components. And so this is, and then there's a 1 over the square root of 2, which is my own pathological normalization. Let's put these indices down. So. Okay, so this is just the component with respect to the basis of self-dual 2 form. So each one of these is at each point is something in the Lie algebra, and this is just a Lie bracket, Lie commutator. So that's the form of the equation. So it's a quadratic nonlinearity. It's semi-linear equations, and one's interested in behavior solutions of these equations. So what can you say about the equations just on general grounds? Well, first of all, as usual, there's a sort of the automorphisms of the bundle P, the gauge group, acts and preserves the equations. So there's a action of the, so there's a kind of a formally a moduli space of solutions, which is a set of solutions modulo gauge transformations. And so if you look at the sort of points in this, the linearization of these equations is Fredholm, at least if X is compact. And so formally you have the sort of whole structure where this is formally finite dimensional, and there's sort of the usual package that you could try to count solutions of these equations and associate some kind of invariant someplace. So this is kind of a proposal, is hey, can we count solutions in some algebraic way in this moduli space and get some kind of invariant? For example, can you get an invariant of a smooth structure on X from this? Well, the problem with counting solutions is that you need to know that you only have finitely many to count, so you're basically interested in compactness of this space. So that's to say, you have a sequence of solutions of the equations. And the question is, what happens? What can you say about solutions to the equations? So let me put this in a historical context. If the phi is 0, which of course you can always set phi equal to 0, then you're just looking at self-dual, then you're just looking at connections, right? There's no phi, and you just have, so this is saying the self-dual part of the curvature is equal to 0, and these are, of course, the famous connections that Donaldson used, what was it now, 30-something years ago, 35, 37 years ago, to define four-manifold invariance. And so, again, Donaldson was faced with exactly the same issue, that you had formally a nice space, moduli space, and you ask what happens if you have a sequence of solutions of these equations. And the question is, what happens? And the answer was obtained actually prior to Simon Donaldson's work by Karin Uhlenbeck's famous theorems. So Karin is, in some sense, the ultimate source of all the analysis or all the analysis in gauge theory can be traced to Karin in some sense. And so what does Karin's Uhlenbeck's theorem say in this context? It says the following, that there exists the following data which describes a limit. So there exists, well, what else? So you have, first of all, some other perhaps different principal bundle over X, and a self-dual connection A prime on this other bundle, and it's self-dual, so the plus part of the curvature is 0. So that's the first thing she gives you, and then second, she gives you a set of points in X, which is finite. Well, if X is compact, it's finite. If X isn't compact, in order to get a finite set, you have to assume initially that the curvature's L2 norms are uniformly bounded. If it's not compact, but let's assume that we have a bound like that. So you get a finite set of points, and then you invariably have to choose a subsequence. So you get a subsequence, we'll call that lambda, of the original sequence. And then the last thing is, well, the solutions are only invariant up to automorphism. So we have a sequence of automorphisms, which we'll call that GI, which I think of these as isomorphisms from the bundle P prime to P on the complement of this set omega. And then, so that's what her theorem gives you, and then the conclusion is, that the subsequence, if you look at the pullback, so now you have a sequence of connections on P prime on a complement of that set omega, that this converges to A prime on compact subsets. Of X minus omega. So you basically get convergence on the complement of a finite set of points. So she geometrically characterizes the failure of compactness as concentration over a finite set of points. And this was sufficient, so in fact you could prove that this kind of concentration, this failure of compactness actually did occur, but even so, that was sufficient for Donaldson to define his four-manifold invariance. So knowing that the lack of compactness had a special kind of geometric flavor. All right, now, so now we're interested in sort of generalizing Karins' theorem or understanding how it changes if we add in this Higgs field, this phi. So the next step in the story was worked out by Ben Mares in his thesis. So Ben Mares, PhD thesis, and Ben studied the behavior of solutions of these equations, but he needed an extra assumption. So Ben studied a sequence of solutions, AI and phi I, subject to the condition that there's an a priori bound on the L2 norm of the phi part. So this is bounded by an energy E, and also if it were non-compact, you'd also need an a priori bound on the curvature norm, if non-compact. Okay, so this is what Ben studied, and under these assumptions, there's an analog of the analog of Karins' theorem is this. So we have more data. We still have the P prime. We have X instead of A prime. Now we have an A prime and a phi prime. And otherwise, the data B and C are the same. We have a finite set and we have a subsequence, and we have these bundle equivalences, and then the statement is almost exactly the same here, that you have convergence of the pullback of the sequence AI converges to A prime, and now also GI converges to phi prime. Oh, and I should say that these A prime is no longer self-dual, but these guys solve the equations. So we have Fa prime plus so it's exactly the same. Well, not exactly, but the analogous statement. So I hope to show you later in my talk where that condition enters. Hope so anyway. But so after Ben's work, the question now arose: well, what if you don't have this bound? What can you say? What can you say if you don't have that? What can you say if you don't have an a priori L2 bound on the norm, L2 norm of the Higgs field? Well, the first question you might ask is, well, maybe you always have a bound like that, and the answer is no, you don't. I mean, there's a counterexample or examples where you can construct solutions where sequences of solutions where this gets arbitrarily large. And so the first of these were constructed a long time ago by Jim Bryan and Richard Wentworth. And what they did was on a Kähler manifold, Kähler form manifold, you can interpret these equations in a sort of holomorphic way, complex analytic way. And then they constructed solutions. And then those were sort of subsequent, actually very recently, further work by Yuji Tanaka and Richard Thomas. And actually they turned out a paper on this over the winter, and then also Gocci and Kuhl turned out a paper, I think, just a couple weeks ago on this. So on Kähler manifolds. So Kähler manifolds, you can sort of say an awful lot, actually. But in fact, there's another way you can see non-compactness, which is you take a three manifold across a circle. And you look for solutions that are invariant under the circle action. So then you're just basically looking at equations on the three manifold. And on a three manifold, the two forms are the same as one forms by the Hodge star. And so on a three manifold, basically you look at an SL2C connection, which is A plus I times phi. So think of phi as a one form. And if that's an SL2C connection, these equations say it's a flat SL2C connection. Okay, so, and then of course we know that there's sequences of SL2C connections that don't converge. The SL2C moduli spaces on three manifolds often aren't compact. So, so we know we have to deal with this problem. Sequences, what happens if you have sequences that, where the L2 norm diverges? So in order to study that, it makes sense to, in order to study sequences of this type, it makes sense to kind of isolate the L2 norm, because that's basically the only thing that can go wrong. So we're going to isolate the L2 norm, and the way it makes sense to do that is kind of renormalize things, divide out by the L2 norm. So we're going to focus instead, rewrite these equations I wrote over there, rewrite these equations for a triple object I'll call R, A, capital A, and little a. So r is a real positive number, just a positive number. Capital A is my same connection. Little a is a section. Again, it's a two-form, a self-dual two-form with values in this adjoint bundle. And the equations I want these guys to satisfy are, well, the first equation is going to be the self-dual part is going to be equal to r squared over 2 a bracket a, and the other part is the exterior derivative of a is 0. And then it will have a third part which says that the integral over x of a squared is equal to 1. So the relationship between the two formulations is that we can write phi as r times a, or if we have a solution of those equations, we write a as phi over the square root of its L2 norm. So this focuses us on exactly where the L2 norm enters. It enters here, and we're going to ask for now studying sequences, which are triples of real positive number, a connection, and a section of that bundle with the property that this positive number diverges. So the question is, what happens? So we have now a sequence of R's, A's, and little a Higgs fields. They satisfy those equations, and I assume that the R's diverge. And now the question is, what happens? Well, let's see what does happen anyway. Okay, so we have some data. So we can now also, we can describe the limit. So I can describe the limit in terms of some data. So first of all, there's some geometric data. Geometric data for the Uhlenbeck compactification was a finite set of points. And in this context, the geometric data is the following. So we have a first piece of geometric data, which is going to be a subset I'll call Z. It's a subset Z in X, which is closed and nowhere dense. And it has a Hausdorff dimension less than or equal to 2. So you think of it as a surface or something that has smaller dimension than a surface. So Z is going to be the bad set. So in Uhlenbeck's, in the self-dual case, Karins says the bad set's are a set of points. Here the bad set is bigger. It could have codimension 2. Okay, that's the first thing. The second piece of geometric data is we'll call I, capital I, and this is a real line bundle over X minus C. Now, when I say a real line bundle, I mean associated to principal Z mod 2 bundle. So real line bundles, it has I think of it as having a sort of canonical locally it looks like R, okay? And it looks like R, it has a metric on it, and you can take covariant derivatives, and you can take exterior derivatives if you have sections of a real line bundle tensor with a differential form. You can take covariant derivatives and exterior derivatives. And in particular, the third piece of geometric data, which I'll call new, is going to be so this is defined on X minus Z, so it's defined on the complement. And this is a a two-form, a self-dual two-form with values in this real line bundle. And it is as closed, so it's a harmonic self-dual two-form defined on x minus z. And then the last piece of data is, and the last constraint is that if I look at the norm of nu, this extends over z as a Holder continuous function. And not only that, but at 0 is actually z. And so where at 0, where nu equals 0, this is the set z. Okay, so the set z is picked out by where this two-form vanishes. Now the two-form itself, this is really saying the two-form itself isn't defined over z because the bundle I isn't defined over z. The bundle z is codimension 2, perhaps. So when you go around a linking circle, the bundle might be non-trivial. So nu technically isn't defined on z, but its norm is, and z is actually where the norm is 0. Okay, so that's the first piece. So that's the geometric data, and then the other, how does that relate to our sequence of solutions? Okay, so what do we need? We need a subsequence, right? So we always have to take subsequences when we look at limits. So we have a subsequence in there, and then instead of having gauge transformation, we don't quite have the gauge transformations, but what we do have is a sequence sigma I, which is an isometric map into the Lie algebra bundle. And these are such that the following is true. So first of all, in terms of convergence, what we're saying is that if I look at the pointwise norm, well, if I look at AI minus nu times sigma I, that this converges to 0. Okay. So pointwise, what's happening is that the Higgs field part is converging to a basically locally a harmonic self-dual two-form times a direction in the Lie algebra. And then you can say some more about how this converges to 0. So this is converging to 0, and then the second thing is a kind of statement about its convergence in terms of integral convergence. So suppose u in x minus z is open with compact closure. Then you can say some things about the integral. So for example, you can say that the covariant derivative, first of all, the covariant derivative of the sigmas, this is integrating over u, that this goes to 0. So the sigmas are trying to be covariantly constant away from z. And then furthermore, the integral over u of the covariant derivative of a minus nu sigma I squared is going to 0 also. So in some sort of Sobolev sense, it's not just pointwise convergence. U is trying to be, the sigmas are trying to be covariantly constant, and the A is in even their first derivatives. And there's somewhat more you can say about it. You can get kind of technical and go into a long song and dance, but the other thing is that the integral over u of the plus part of the curvature is also converging to 0. Now, you can't say all that much about the minus part of the curvature except under certain circumstances, but if it's a compact manifold, you can say that the full curvature is trying to commute with these sigmas. So this is going to 0, and then various other second derivatives are going to 0. So there's various higher and higher sort of order convergence, you can say, on the complement of the set U. So what's happening is that there's a bad set Z, which is sort of morally looking like a surface and some lower dimensional stuff. And on the complement of that bad set, A is trying to align itself in the Lie algebra. All the components of A are trying to align themselves with respect to this part, the Lie algebra, and the connection is trying to be reducible. And the self-dual part of the connection is going to 0. And that's basically what I can say about the limit. It's not clear that I can actually say that the connection itself is converging. But at least it's some aspect of it is converging. Now, the question is, whether this is good enough to prove theorems about four manifolds. So that's for the next 50 years of JDG. So I don't know if it's good enough to prove. So far, no, but maybe it's a start. I don't know. Okay, well now I have some 15 minutes left maybe. So what I'd like to do is somehow indicate why all this is true. So the details are, of course, a bit messy, but maybe I can give you some indication of where this data comes from. Where the sigma comes from, and why the Z is codimension 2. Of course, this is all in hindsight, right? I mean, this isn't how one thinks about it over the, so you spend like 5 or 6 years thinking about a problem like this. Those of you who are youngsters. So you realize that one thinks about this over 5 or 6 years, and then after sort of figuring it out, then there's a kind of evolution of your understanding, and then afterwards, after the fact, you sort of see that why you were so stupid for 5 or 6 years and why you should have seen it immediately. So I'm going to present after the fact, but don't make the mistake of thinking that this came like full blown out of somebody's head. This is only after the fact. So Harvard was, famous for Raoul Bott, was one of my mentors at Harvard. And Raoul used to say, doing math, proving theorems is like going downstream on a canoe. Those theorems just kind of flow. And I sort of was scratching my head, and I said, well, maybe that's the way it works for you, but for me, it's paddling upstream all the way. But anyway, so let's see, why should this be true? So you start out this equation, so there's a sort of Weizenbach formula. You make it into a second order equation, and then you commute derivatives, and this is where the magic of this term comes in. That's sort of why that term is so beautiful. So I don't know, somehow this had to do with, I don't know, Qumran, n equals 4 supergravity. I don't know, what did it come from? But anyway, somehow, nature knew to make this term. Or Qumran and Witten knew how to do it. But anyway, you get an equation like this, and then there's a double commutator, and I'll write the components with a little c. So this is implicitly summing over components. So let's forget this. So this is the Riemannian curvature term. That's basically irrelevant to everything. Well, not quite irrelevant, but anyway. And this is the r squared, and then this term is a double commutator. I'm summing over c. And so it's a double commutator. And to see what that does for you, let's take the inner product. This is a trace Laplacian, so this is just a covariant Laplacian there. So you can take the inner product of that with A and integrate by parts. And when you integrate by parts, you get an identity which says that the covariant derivative of A squared plus a term, and then this term, which is the bundle curvature term, turns out to be positive. It's just this. And then there's this metric term, which I'll put on the other side as minus the inner product of A with R times A. So that's kind of a beautiful thing because, because this R is just it's just bounded. And so this term A, if R, for example, is positive, definite endomorphism, then that side would be negative and this side would be positive, and you'd know you didn't have any solutions at all. So if you have some curvature inequality, curvature positivity of the appropriate sort, for example, the force sphere, you won't have any solutions. But usually you don't have this curvature inequality, but in any event, this is uniformly bounded, and then you just get something which is bounded by A squared, which is bounded by 1. So there's some universal constant I'll call C0. There'd be the integral of A squared here, but that's equal to 1. So you get this a priori bound on this, and then you notice this term is, it's almost a L2 norm of that term. So that term over there, that term is also the integral. You can write it as 1 over R squared times the integral of the plus part of the curvature squared. So that's bounded by a constant. So for example, if you knew the R's weren't getting very big, if the R's were bounded, that would tell you you had an a priori bound on the L2 norm of the plus part of the curvature. But then you'd have an a priori bound on the L2 norm of the minus part of the curvature, because the difference between the plus part and the minus part is a Pontryagin, is a characteristic class. I forget, 4 pi squared or 8 pi squared or something times the second Chern number of some bundle associated to the principal bundle. So then you'd have an L2 bound on the whole curvature, and then you could say, call up Karin Uhlenbeck and say, what do I do? And she'd tell you what her theorem was. Say, look at that paper I wrote back in 1980. And you'd find that the curvature, the connection converges after you do appropriate automorphisms. You'd have a sequence of connections that converged on the complement of a finite set of points. Complement of a finite set, omega, in the L21 topology, so L21 weak topology, Sobolev topology. But anyway, that convergence would be enough because you also have an L2 bound on the covariant derivative A. That kind of convergence of the connection would tell you that this guy converges in the L21 topology. And then once you have L21 convergence, then you can bootstrap to L22 convergence and L23 and blah, blah, blah. And then you get Ben-Mayr's theorem, almost, practically. You can mumble something about elliptic regularity and get Ben-Mayr's, right? So people mumble elliptic. They say, oh, I do this too. You say, oh, it's in chapter 6 of Mori. I made this joke. Yao corrected me on this. I said, you're using your paper. It's in chapter 6 of Mori. Nobody alive knows everything that's in Mori's book. So nobody can say it isn't in chapter 6 of Mori's book. So, and then Yao told me that actually, in fact, in the last chapter of Mori's book, he said Mori invented spectral sequences in his book. Anyway, anyway, so you mumble something about elliptic regularity, and then you use Karin Uhlenbeck's theorem, and you're done. But if the R's go to, if R diverges, then then you don't have any bound on the curvature anymore, and so you're sort of in terra incognita. But one thing you can do, see, you can use, you can get more information on this in the following way. You see, these covariant derivatives are metric compatible. So, that means that the usual derivative of the norm of A is less than the covariant derivative of A. So that's sometimes called Kato's inequality. And actually, but it's just saying the thing is metric compatible. So that means that you actually have an L2 norm on the norm of the norm of the Higgs fields. So that tells you that the AIs, so you also, of course, their L2 norm of the Higgs field themselves is 1. So there's some subsequence just converges weakly in L2-1 to some function, which turns out to be the norm of what I was calling nu. So we'll call that limit nu, norm of nu. So you get weak convergence to some function already, and actually you get better than that because, so here I took the inner product with A and integrated by parts, but I can take the inner product with any function times A. And it's convenient to take the Green's function for a Laplace operator. So you could take the Green's function for this. So we call it the Green's function with pole at P, which is a delta function at P. If you take the inner product with A and then multiply by the Green's function and then integrate by parts, that you find out that you have an a priori bound on the, not just, you have an a priori bound like this. Is less than this constant, which is universal. So not only is this function in L21, it's actually in L21, and it's L infinity. And now that's kind of an interesting thing because, see, this is the commutator of the components of A, and it has an R in front of it. And so when R gets very large, if this side is uniformly bounded, it means the components of A have to commute more and more. So this is telling us that, in some sense, the components of A should be, they should be more and more commuting. So the various components of A should want to commute over more and more of the manifold. So this should be on the order of 1 over R. Now, if you imagine that the components actually did commute, so if you assumed that the components actually did commute, if you assume that they did commute, that would be saying that the one form A is a two form is a Lie algebra element times, at least locally, a real value 2 form. And then if you impose the condition that its exterior derivative is 0, that's saying that d nu times sigma plus nu wedge dA sigma equals 0. And if you normalize this so that the sigma has norm 1, which you can always do at the expense of the norm of this guy, then this is orthogonal to that pointwise, and so that tells you that d nu is equal to 0 and the covariant derivative of sigma is 0. So here's where we get our harmonic form, our locally real valued harmonic form, if it in fact is the case that these guys really want to converge pointwise. And we also get our sigmas being, remember here, the sigmas want to be covariantly constant. So the problem with all this analysis is, of course, this is assuming, I mean, this only works, I mean, this wants to be small most everywhere, but the question is most everywhere might be it might be dense. Most everywhere might not, where this doesn't work is where A is small. If A is on the order of 1 over r squared, then whether or not these components commute or not isn't going to make much difference to that constant. So the question comes down to this. I mean, it may be that A, well, we know it's L2 norm is equal to 1, but the question is, where is it nearly 1, where is it going to 0? So if it's going to 0 in lots of places, which is very dense, and in the limit, everything, you know, it's kind of a dense set, then all this doesn't do you any good. So the whole crux of the matter is to show that it's not going to 0 on some horrible set. So that's really the hard part. And I'm out of time, so I don't have time to tell you how to do that, how to show that. But anyway, but that's the story. And I should say that this kind of analysis, this discussion of a limit in terms of a sort of harmonic form or harmonic spinner or something on the complement of x minus z with values, a spinner or a form with values in a line bundle, this seems to be a characteristic limit of these kind of 4-dimensional Higgs, 3- and 4-dimensional Higgs equations, where you get a limit that's described geometrically by codimension or Hausdorff dimension 2 set Z, and on the complement of it some kind of harmonic form or harmonic spinner whose 0 locus is formally a set Z. Okay, I'll stop. I'm out of time, so I...